All right. Hello. Welcome. Been a while since I recorded a video. Hopefully I'm not on mute. That would be terrible. Should have done a test run, I guess, but I'm just gonna jump right into it. So last day we were working through the what's it called? Systems of linear equations notes. And we were working on example 2 on the second page, and I kind of left you to work through it. In fact, I even said, okay, now you have all these skills already, so you could work through all the problems. But today I've decided we'll just work through these problems and we'll save matrix algebra for next week, because I think that'll be better together. And so we're just going to work through these, the rest of these notes. In fact, I'm going to leave from example 7 onwards for you to try on your own. I'll post the notes, but I think once we've done all these examples together, you'll have all the skills that you need to do the rest. Okay. So we were working on example 2, which said to use a matrix with elementary row operations to solve the system. And so the first thing that we do is we set up this system of equations as a matrix. And so we use the coefficients, and we talked about last day how that's a little bit easier than carrying the X's and Y's and Z's forward. And then we separate the equal sign essentially with this vertical bar, to show that, okay, the solutions are here on this side. Now our goal, and there are many ways that we can get there, but our goal, right, is to get that diagonal form where we have a 1 for the coefficient of X and then 0, 0 for the coefficients of X or for Y and Z. And then we have the solution for X. Same thing, we're looking for a coefficient of 0 in the second line for X, but then a coefficient of 1 for Y and a coefficient of 0 for Z. So then we have the solution for Y, and then same thing, 0, 0, 1, and then we'll have the solution for Z. So that's our goal. And there's lots of ways, depending on how your brain works, right? You might see something that's really easy, kind of a quick win, go for those. Just make sure that if you have a 0, try to keep it a 0. Don't undo any zeros, right? You don't want to be doing that. And so what did we do? We started, and just as a recap, we're allowed to move rows around, right? Switching that this is row 1, row 2, row 3, doesn't matter. This could be row 1, row 2, row 3, it doesn't matter. And so we'll see an example where we have to switch the rows. What else are we allowed to do? We're allowed to multiply or divide by any number, right? And so any value that makes it convenient, usually turning things into a 1 is what we're doing. And we're allowed to add or subtract any multiple of a row to another row. Okay? And how we indicate that is by using kind of R1 to denote row 1, R2, row 2, R3, obviously row 3. And so here, first thing we did, I didn't see any quick wins or any rearrangements that would save me any work. And so here I said, okay, what I'm going to do is I'm going to turn this 3 into a 1 by dividing this entire row by 3. Luckily, I glanced ahead and I saw that they were all divisible by 3. If they're not divisible by 3, I might hold off on making that move. But in this case, they're all divisible by 3, and so I get 1, -2, 3, and 0 divided by 3 is still 0. You want to make sure that you do your manipulation on this side of the vertical bar as well, right? Otherwise, you'll be missing the equal sign. Okay? It's not equal anymore. So then what we said, okay, in this case, in this move, nothing happened to row 2 and nothing happened to row 3. So you just rewrite them out. I want you to write them out just because then you're not going to get lost. eh? And what I mean by that is coming up here. So then we said, okay, now I'm going to take this 1 and I'm going to use it to eliminate this 4 and this -2 in the coefficients for x in the other two rows, right? I want to turn these into zeros. That's my goal. And so what I'm going to do, right, I turn this into a 1, and to eliminate this 4, to turn this into a 0, I would need to subtract 4 times row 1 from row 2. So how we wrote that was R2 minus 4 times R1. And so this tells me that R2 is being manipulated. And in this case, to save a little bit of work, this was the first time we did it, I think. I don't think we did it in the example, but we said, okay, instead of just writing out row 3 unchanged and then changing row 3, because the change to row 2 and the change to row 3, they're independent of each other. And so then I can do them in the same move. I know, a little bit cheeky, but you'll see once we've done enough row operations, which is what these are called, you're going to want to cut corners when you can. Okay? And so what we said here, to get this -2 to turn into just a 0, then I need to take row 3 plus 2 times row 1. And you need to do it for each of the terms, right? None of the other ones usually go to 0. But if we're lucky, they turn into something nice. Okay, so we got row 1 stayed the same. And our goal was to change the coefficients of in the x column, right? We can think of this as kind of x, y, z. Right? They're there, but they're not written out. And so now our goal was to turn these into zeros. And once we have these zeros, we don't want to let them go. You don't want to do an operation where it's going to kind of undo those zeros. That would be bad, right? So something to keep an eye out for. But if we move in this direction, usually it works out. So jumping in here, what do we have to do? Now I'm going to do the same thing, and I'm going to turn this 2 into a 1. And then I'm going to pivot around that 1. But first I need to turn it into a 1. And then in the next set of row operations, I can turn this into a 0 and this into a 0. Right? So sometimes, or often I should say, we circle the one that I want to turn into a 1. Right? And oops, that was a little shorty arrow. To turn that into a 1, to turn 2 into a 1, I'm going to take 1/2 times row 2. Looks like I didn't have lines before. Maybe I'll do full 3 lines. I should have made smaller lines, maybe. Yeah, whatever. Okay, row 1 unchanged. 1, -2, 3, 0. Row 2 is the only one being manipulated. 0 divided by 2 is 0, so that's good. 2 divided by 2 is 1. -4 divided by 2 is -2, and -4 divided by 2 is still -2. And row 3, unchanged. 0, -5, 7, 7. Nice. Okay. Now we need to, whoop, it zoomed in on me. There. We need to use that 1 to eliminate the y coefficients in the other two rows, right? And so first, And because I can manipulate row 1 individually and it doesn't affect row 3, and same thing, I can again manipulate row 3 without affecting any of the other rows, then I am going to do them in the same maneuver, right? Just like we did earlier. Oops. So to change -2 into a 0 now, we're using 1 from row 2. I need to do row 1 plus 2 times row 2. Uh, Okay. This is where you need to keep your wits about you. And so 1 plus 2 times 0 is 1. That's good. -2 plus 2 times 1 is 0. That's also good. That was our goal, right? That was the one that we were chipping away at. Okay. And so now 3 plus 2 times -2. 3 minus 4, -1. And I better have my cheat sheet out because what a mess that would be. Looks like I'm good. I was able to do 3 minus 4. Feels good. And then 0 plus 2 times -2. So 0 plus -4 puts me at -4. Okay. This one, maybe I'll still keep it green to show that it's staying the same from before. And getting really spicy with the colors here. How about this? Change it. And then I can use orange for the third row. So to change this -5 into a 0, I have to do -5 plus 5 times row 2. So row 3 plus 5 times row 2. Again, 0 plus 5 times 0 makes 0, so that's good. -5 plus 5 times 1. Oh, hey, erase. What's fun is when I'm filming, I can see, so I look at my shared screen a lot to see what you're seeing. And so usually in class, you can't see the pens that I'm choosing between. So that's kind of nice. But I also got used to it. So used to keeping it secret. So now I'm trying to make this 0. So hopefully it's 0. So -5 plus 5 times 1. Phew. Then 7 plus 5 times -2. I'm going to get -3. And same thing because I have the exact same scenario, right? 7 plus 5 times -2, -3. Where can I put these? Should put them here. Now you know. I'm looking over here, I'm cheating. I'm looking over here. It's fine. Just looking at my screen. Okay, so regrouping. All good. Now what? Last thing, same thing, but again, now we're gonna pivot around. What color can I use? I'll just use orange again. -3, I'm gonna have to turn it into a 1. You know what? Let's just use dark blue. -3, to turn it into a 1, I'm going to divide by -1/3, so -1/3, or not divide by, multiply by -1/3 times row 3. Row 1 stays the same. 1, 0, -1, -4. Row 2 stays the same. 0, 1, -2, -2. And row 3, 0 divided by -3 is 0. Same thing again. And then this one, I need it to turn into 1. So let's just make sure -3 times -1/3. It does equal 1, which means that this equals 1 as well. Good. Now, we're so close. Our last move. We have to pivot around this 1 to eliminate the -2 as well as the -1. Yeah. And this is kind of the home stretch, so let's see what we can do about it. Again, I'm going to do the same thing where I manipulate row 1 and row 2 in the same on the same arrow kind of deal. And so for row 1, I have -1. So if I have -1 plus 1, then I get to 0. So that's nice. So it's going to be row 1 plus row 3. I can do that. 1 plus 0 is 1. 0 plus 0 is 0. -1 plus 1 is 0. That was our goal. What we're really interested in is -4 plus 1. Right? -3. Same thing with row 2. To eliminate -2 and turn it into 0, I'm going to add 2 of row 3. So row 2 plus 2 times row 3. 0 plus 2 times 0 is still 0. 1 plus 2 times 0 is still 1, so that's nice. And then -2 plus 2 times 1 makes 0. And same thing, -2 plus 2 times 1 also makes ba, 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 ba. I did it the wrong way. -2. Yeah, makes 0. It still makes 0. 0, 1, those were unchanged. And then I did get -2 plus 2. Good. And then -2 plus 2 again is 0. Then row 3 is unchanged. Finally, this is in what we call reduced row echelon form. I'm not going to call it that because I haven't seen it mentioned in the textbook, and so that's okay. But if you're kind of Googling things, it's called reduced row echelon form. Now, I see that x must be -3, y must be 0, and z must be 1. So therefore, x equals -3, y is 0, and z equals 1. You can always check your work. I'll add a page here. Because this solution should satisfy all of these simultaneously, right? And so check your work. Three times -3 minus 6 times 0 plus 9 times 1. Does it equal 0? It does. -3 times 3 is -9 plus 9 makes 0. Eee, that's good. How about the next equation? 4 times -3 minus 6 times 0 plus 8 times 1, does it equal -4? -12 plus 8 does equal -4. Whee! Feels good. Just one left. Let me guess, it's going to work. Yes, of course it is, because we did it right. If I can write it down right, -2 times -3 minus 0 plus 1. Does it equal 7? -2 times -3 makes 6, plus 1 is 7. What a relief. Phew. So it works. All right. You get to celebrate. Okay. Awesome, awesome. I even wrote it in the notes, right? When you're done, it's always a good idea to just plug these values into the equation and make sure that they actually solve the system. It's nice because you have the answer key, right? You just don't know what the values are, but once you have those values, you can always check them and make sure that they work. And so that's nice. We haven't used the first elementary row operation where we can interchange two rows, but sometimes we need to. And so our main goal, right, is to end up with a diagonal of ones, which means that we're always going to need a value of x in the coefficient in the top row, a value of y as a coefficient in the second row, and then a z in the third row at least. Okay, and so sometimes we need to rearrange things until we get how we want it. Now there's lots of different ways that we could do it, right? And so let's try this example here. Now I'm going to put it up top because otherwise there's a whole page here. But the rest of the page does talk about pivoting, but we've already been calling it pivoting and we've already been doing it. And so that's, that's old news. What's pivoting? When we turn something into one and then we eliminate the others around it using the one. That's pivoting. Pivotal. No. Let's see here. Need my cheat sheets, because this one, it's kind of a choose your own adventure. For this one, what's the first problem? If I rewrite this matrix or as a matrix, it would look like this, right? I have 0, 1, 1, 0. 3, -1, 1, 6. 6, 0, -1, 7. Now, I do want to make sure, because what I did when I made up a question, I was trying to make it solvable and then I made it not solvable. So 0 and 1, 0, 3, -1, 1, 6, 6, 0. Good. So the problem is here, right? I need to have a value of x here so that I can turn it into 1. There's no way I can do anything to manipulate this into a 1 easily. I mean, I could add row 3 to row 2, but I think it's easier to just swap them. And we could have just as well swapped row 3, but I don't know. There wasn't any benefit that I saw. But maybe you see it. When we swap rows like this, we use a little double arrow to indicate it. And so then what we get is 3, -1, 1, 6. 0, 1, 1, 0. 6, 0, -1, 7. Now we have a new row 1 and a new row 2. Nice. And from here, we have to kind of plan ahead a little bit, be a little bit strategic with our moves. Now, my issue here is if I divide by 3 just blindly, which you absolutely can do, that works for this 3, but then I have negative 1 over 3, 1 over 3, 6 over 3 works, but I would have to deal with these fractions and I would have to work with the fractions, which you absolutely can do. You know how to work with fractions. That's not the problem. They're just kind of sticky and ugh, I don't like working with them. But remember this, the main goal is just to eliminate this value, turn it into 0, no matter what cost, right? And so what I'm going to do, sneaky, is I'm going to take the 3 and use it to eliminate the 6, right? That comes with practice, and if you don't see that right away, that's fine. But eventually, like I said, you're going to kind of seek out kind of shortcuts, right? But as long as you play by those 3 elementary row operations, you're allowed to do them in any order, and you're allowed to do whatever you want. Okay? So for me, kind of sneaky is to take row 3 minus 2 times row 1. What's nice, though, is there's already a 0 for the first coefficient in row 2, so I don't need to deal with that. So I'm just going to focus on this kind of sneaky maneuver. Row 1 stays the same, right? The one that's being altered is R3. So 3, negative 1, 1, 6. Row 2 stays the same as well. 0, 1, 1, 0. And it's only row 3 that's being changed. And so row 3 minus 2 times row 1. So 6 minus 2 times 3 does make 0. Oh, maybe I'll use pink. Now I have 0 minus 2 times negative 1. Now minus and negative makes plus, and so 0 plus 2 makes 2. Now I have negative 1 minus 2 times 1 is negative 3. And then 7 minus 2 times 6, 7 minus 12, negative 5. Let me just confirm here. Looks good. Okay. So you're allowed to do it even if you haven't turned it into 1. It's just often the math is the simplest if you've turned it into 1. In this case, not really, right? So now what? I'm going to hold off on turning this into a 1. I can hold off for a little bit, right? Until I've turned this into 0 and this into 0. Then my final maneuver might be to turn this into 1, right? Because I do need it to be 1 to find the solution for x. But when I do it is kind of up to me. And so for me, I have a 1 here. And so that'll be nice, right? I can pivot around this 1 and I can add row 2 to row 1 and I can subtract 2 times row 2 from row 3. Better in writing, I think. So I'm going to do row 1 plus row 2. And then I'm also going to manipulate row 2 minus 2 times row 2. Nope, row 3. minus 2 times row 2. Putting me at, I'll deal with row 1 first. 3 plus 0 makes 3. -1 plus 1 makes 0. That was the goal, so that's good. 1 plus 1 is 2. And 6 plus 0 is 6. Row 2 remains unchanged, so I'm just going to jot it down, 0, 1, 1, 0. And row 3 is going to take row 3 minus 2 times row 2. So 0 minus 2 times 0 is 0, so that one's fine. 2 minus 2 times 1 is 0. That was the goal, so that's good. Let's jot those down. -3 minus 2 times 1 puts me at -5. And then -5 minus 2 times 0 is still -5. So that's cool. Add a page here. Nice. So next thing we're going to do is we are going to turn this into a 1, right? That might be nice to deal with. And then we're going to eliminate these last two and then divide by 3, and then we're done. Just like that. So here we go. To turn -5 into 1, I'm going to take -1 divided by 5 times row 3. And the other two rows remain unchanged, but you want to write them with a little bit of spacing, not smush them like I just tried to do. 0, 1, 1, 0. And 0 divided by -1 or times -1 over 5, 0, 0, 1, 1. Score. Easy. Now I'm going to pivot around this 1 and turn this into 0 and this into 0. Row 1, 2 minus 2 times row 3. And while we're at it, row 2 is going to be R2 minus row 3. I find working with matrices is really relaxing because you can just plug away at it and eventually you'll get there, right? You're just doing the same thing over and over and over again. And so row 1 minus 2 times row 3. So 3 minus 2 times 0 still is 3. 0 minus 0 is 0. 2 minus 2 is 0. That was the goal. 6 minus 2 is 4. Row 2, 0 minus 0 is 0. Or row 2 minus row 3. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. And 0 minus 1 is -1. And row 3 is unchanged. 0, 0, 1, 1. Now, the very last thing we need to do here, we left that as a 3, but let's divide that and turn it into a 1 now at the very end. Row 1, multiply it by 1 over 3. And I get 1. 0 divided by 3 is 0. 0 divided by 3 is 0. 4 divided by 3, I'm just going to write 4 over 3. Doesn't matter. And the others stay the same, 0, 1, 0, -1, 0, 0, 1, 1. Finally, it's in diagonal form, so therefore x is 4/3, y is -1, and z is 1. Nice. Okay. Good. We're going to check our work because we have the answer key, so we may as well use it. Let's see here. Try to put it on their own lines. Kind of hard. Is -1 plus 1 equal to 0? Yes, it is. Oh, hey, where'd it go? Yes, it is. How about is 3 times 4/3? That's nice because that's going to cancel into 4. Minus -1 plus 1, is it equal to 6? Let's see. 4 plus 1 is 6. Score. And then finally, is 6 times 4/3 minus 1 equal to 7? 6 divided by 3 is, let's see here, 2. So then 2 times 4 is 8, minus 1 is 7. Can you imagine if that hadn't worked? All right. Nice. And if I was able to share or I've actually looked for an app version of our calculator or some version of this calculator, or any kind of engineering calculator, but I can't find one. It has to be free because I'm cheap. And so I don't have it. But your calculator does have a function where it can solve a system of equations. And so I showed you last day. And so that's worth exploring, kind of Googling your calculator and how to solve systems of equations. And if it can do it, there's a YouTube video on it, I'm sure. So worth looking into. It's here. Okay. All right. So we did the sky up above. See work above. So like I said, here we define pivoting, although we've already talked about it and used it a lot. So in order to transform a matrix into diagonal form, remembering that's our overall goal, we select a term and we eliminate other coefficients in that column. And so when we're doing that, even when we use the 3, it's still called pivoting. Yeah? And so often we transform it into 1, but you don't have to. Most commonly we do. Yeah? But we transform all the other entries or coefficients in that row or in that column, sorry, um, into zeros based off of the one we're pivoting around. And so in terms of pivoting, what we're doing is we're doing Gauss-Jordan elimination, right? Still, but with matrices. And so what we can do is, or what we have been doing is we write down the matrix that corresponds to the linear system. And then we make sure that the first entry in the first column is non-zero, just like we did in the previous example, right? Which means you might need to interchange rows, maybe, okay? Or maybe there's an easier row to use as your first row, right? If you have a coefficient of 1 somewhere, usually I float that to the top. Less work. And then you pivot the matrix around that first entry, and then you move on to the second column, right? Make sure it's non-zero so you have something to work with, and then you pivot around those, and then you keep going until you have everything in diagonal form. So far, we've only seen systems with a single unique solution. That's not always the case, of course. And so it's also possible to find that a system has no solution or infinitely many solutions. And so we're going to consider each by example. And so, but first, before we do these examples, I just want to show you what it looks like. So when we have three variables, x, y, z, what that looks like is this kind of 3D situation, right? X, y, and z. So a combination of x, y, z, if we moved A units on the x-axis, B units on the y-axis, and C units on the z-axis, then we're at a point at ABC. So now we're going to be dealing with planes instead of lines intersecting, and that becomes really difficult to imagine, right? But what it looks like, so that's why I wanted to show you. And we can solve systems with more than three variables, but then we can't visualize it. We can still solve it, but we can't visualize it. So if you have a unique solution, that means that at some point, so at some point in the universe, right, these planes intersect perfectly and there's just the one solution. Yeah? And so that means that you have some, let's see here, some x coordinate, some y coordinate, and then let's call this your z maybe, right? And so just at this one little point here, in here, is your one solution, your x, y, z values. Right? It is possible to find that there is no solution, right? Something like this, right? Where the green and the blue planes never intersect, right? They're parallel to each other. And so, yeah, the red plane does intersect both, right? But not at the same time. And so that's what it means to, or that's what it looks like to have no solutions. There's no point where the green and the blue plane intersect, right? And so there is no solution. On the flip side, if you have infinitely many solutions, right? You've got the blue plane and the green plane and the red plane. Well, all of these points are solutions. And depending on how thoroughly you measure, right, we can go in infinite depth there. And so that's why we say there's infinitely many solutions. And of course, usually these planes go to infinity as well, right? Positive and negative infinity. But so then we would have all these solutions to choose from. You know? So let's do some examples to see what. Okay, spoiler alert. The first example is going to be a unique solution, and then I'm pretty sure I have no solution followed by infinitely many solutions, but let me check. That is what I did. Wow. It's almost like I am predictable. So should I do 4? How about this? Because we just did one with solutions. So we know what the ones with solutions look like. I'll leave space, but how about we jump straight into one where there are no solutions. I'm telling you there are no solutions, but we have to figure out what that looks like in terms of, okay, when I'm solving this thing, what am I going to run into? So we solve it the same way. Let's get to it. First, we write this thing out as a matrix. I'll do it up here, why not? 6, -2, 2, and 4. 3, -1, 2, and 2. And let me just double check here. -12, 4, -8, and 8. Okay. Let me just check. Looks good. All right. So, first thing I'm going to do is I'm just going to keep this and use it and turn it into a 1, and then I'm going to pivot around it. Yeah. So that's the first thing I'm going to do here. 1/6 times row 1. All the other rows can stay the same. So I guess I'm staring down the barrel of -2/6, but you know what? We can handle it. We can handle fractions. Let's do it anyways. Is there a sneaky way around it that you can see? Could do something crazy like 6 times 1/2 to eliminate the 3, and then 2 to eliminate the 12, but uh, let's just go kind of brute force on this thing. Turn the 6 into a 1. See what happens. You're always allowed to change your mind, start over. But 1/6 times R1 makes 1, -2/6, and +2/6, and 4/6. You can simplify those if you want to. Um, but let's just leave them 3, -2, 2. So row 2 and row 3 are unchanged. -12, 4, -8, and 8. So now, next thing, just kind of going through the same procedure that we have been doing is, okay, if I need to turn this 3 into a 0, then I'm going to take row 2 minus 3 times row 1. Row 2 minus 3 times row 1. What am I going to do to row 3 while I'm at it? And maybe I'm just going to shorten this up and tighten this up a little bit. Row 3, -12 plus 12 times row 1. So row 3 plus 12 times row 1. Let's do it. 3 minus 3 makes 0. I'll write out row 1. Uh, let's simplify -2/6 because I'm multiplying by 3. You don't have to, but you can. Oh, it looks like that's what I did anyways. -1/3, 1/3, and 2/3. -1 minus 3 times negative 1 over 3. Let's use this one. These are the same. I just simplified them, right? So I'm not actually making a change here. Negative 1 minus 3 times negative 1 over 3 makes plus 1. So negative 1 plus 1 is 0. That's a bummer. How about negative 3 times 1 over 3 is still going to be 1. So 2 plus 1 is 3. And then we have 2 over 3 times 3 is 2, but I have 2 minus 2 then makes 0. That's the problem, isn't it? I think we found it. I know we found it. Um, I'm not even going to bother with the rest of the row operations because there's no way out of this, right? The problem here 3z is equal to 0, but 3 can never be 0. Huh? So since 3 is equal to 0, right, this is a contradiction. Or since 3 does not equal 0. Or maybe I want to, sorry, not this. Since 3 equals 0 is a contradiction, there are no solutions. There are no solutions. So then you're done. Mm-hmm. And that's how you know if there's no solutions. Still trying to think. Oops. I want to check something. So I'm going to pause it. Doesn't make a difference to you. I found the problem. I jumped the gun. Why? And the reason it had me kind of second guessing myself was because if we translate these into linear systems, then x times 0 or 0 times x, 0 times y plus 3 times z, it can equal 0, right? If z is 0. So that's not the contradiction. I don't know where or what I was thinking when I wrote that. So then I did a little Martha Stewarting here, and well, I actually doubt that Martha Stewart works with matrices that often, but we should find out. But then I kept going because I thought, oh, okay, well, I mean, it gets a little weird here because we have nothing to pivot around for the y, so that's kind of an indication that there will be a problem. But even if you kind of stick to your guns and you pivot, I decided to turn this 3 into a 1. So by dividing that row by 3, and so then if I keep going, so this is my erratum, my official error correction. Mea culpa. Turn it into a 1, and then if I pivot around this 1, then I can take away, this is 1 over 3. I was just working on my own there for a bit. So R1 minus a third times R2 makes it 0, but I am left with two values here. So 1 times x minus 1 over 3 times y plus 0 times z makes 2 over 3. We can still handle that, right? The problem is this, right? So when I pivot around this 1 and turn this -4 into a 0, what I find is that this is the contradiction, not the previous one. Oh my gosh. Contradiction. Yeah. Since 0 times x plus 0 times y plus 0 times z can never be 16. That's where it is. That's what I was hanging on. I jumped the gun. Something equals 0. Well, that's allowed, but 0 plus 0 plus 0 can't be a number except for 0. Ah, my bad. Oh well, you live and you learn. And maybe I should snag this summary. This is where I had to refer to. So here, no solutions. If at any time one or more rows is of the form 0, 0, 0, so all zeros, gives an answer of A, okay, where A is a non-zero number. It's fine if it's 0, right? That's true. Non-zero number, then the linear system has no solution. So if you do your work and you find that, okay, you get a row of zeros, but it equals a number, there's no solution. Okay. And my first go-to is checking it on the calculator, but then it just said no solution. That's not very helpful. So then I had to go through and do the work. Boo. Okay. This one, I'm telling you, will have infinitely many solutions. So what's that gonna look like? Let's see. First, let's write out our matrix 2, 2, 4, 8, 1, -1, 2, 2, -1, 5, -2, and 2. I don't really feel like issuing an erratum again, so let's see here. 1, -1, 2, 2. Okay. All right. Let's see here. You could do something sneaky, like you could switch row 1 and row 2, and then you just have a 1 here. That's fine. These are all easily divisible by 2, so I'm just going to go ahead and do that instead. But like I said, matrices are kind of choose your own adventure type of situation. So um, whatever jumps out at you as making the most sense, remembering your overall goal of that diagonal form. So then I get 1, 1, 2, and 4. In the first row, the other rows stay the same. 1, -1, 2, 2, -1, 5, -2, and 2. I'm going to pivot around row 1. And at this point, we're fairly familiar, right? Row 2 minus row 1, and then row 3 plus row 1. Row 1 stays the same, 1, 1, 2, 4. And 1 minus 1 is 0. -1 minus 1 is -2. 2 minus 2 is 0. And 2 minus 4 is -2. Moving on to row 3. -1 plus 1 is 0. Good. 5 plus 1 is 6. And -2 plus 2 is 0. And 2 plus 4 is 6. This also looks weird, doesn't it? It's supposed to look weird. Okay. But let me just make sure it looks weird in a good way. It does. So if we kind of forge ahead, what am I going to do? I'm going to turn this -2 into a 1 by dividing by divided by -2. So let's do that here. -1/2 times row 2. Row 1 stays the same, 1, 1, 2, 4. Row 2 is the one that's being altered, 0, 1, 0 stays 0, and -2 divided by -2 makes 1. And row 3 stays the same, 0, 6, 0, 6. You can probably already see the pattern, okay, but we're going to follow through. And so we have this one that I'm going to pivot around. So row 1, I'm going to subtract row 2, and from row 3, I'm going to subtract 6 times row 2. Row 1, I get 1 minus 0 is 1, so that's good. 1 minus 1 is 0. 2 minus 0 is 2, and 4 minus 1 is 3. Probably easier if I just don't read out the math, because I trip myself up, but that's okay. Row 2 stays the same, 0, 1, 0, 1. And row 3 minus 6 times row 2 is 0, 0. And then 0 minus 6 times 0 is 0. And 6 minus 6 times 1 is 0. Phew. Okay. That's a true statement, right? This is a true statement. That was the problem before, where we had 0 plus 0 plus 0 equaling some number, but 0 plus 0 plus 0 is always 0, right? And so this is a true statement. True. Because 0x plus 0y plus 0z is 0 for any values of x, y, z. And so that's how we know we're going to have infinitely many solutions. Therefore, we have infinitely many Mm. Solutions. In fact, let's see here. Uh, they don't have a nice summary there. So then the solutions, we have solutions. In fact, we have infinitely many solutions are going to look like this. So infinitely many solutions we can't pivot around this 2. I mean, we could divide this row by 2, but then I'm left with 1/2, and that doesn't really help at all. So what I'm gonna do is I'm gonna rewrite this as x plus 2y is equal to 3, and, or sorry, 2z is equal to 3, and then y is equal to 1, and z can be anything. Uh, x plus 2 times z is equal to 3. And y is equal to 1. And z can be any value. And I'll move this over here. Right, I can plug in any value of z, right, because that's the one that's empty here. And x will correct itself, and whatever the value of z is, it'll correct, and it'll force x plus 2 times z to be 3, right? Y is 1, so y is fixed at 1, and x will correct itself depending on what value of z you plug in here. Okay, nice. So, oh yeah, the notes are up here. What I'll do now, uh, mostly because I have to go pick up my dog from doggy daycare. So what I'll do is I'll add these solutions to the notes, but this is the only one that I was going to do with you guys, but I think you can work through it on your own. And now you can read the solutions and they'll make more sense. You can follow along. Um, and then I've got more examples for you to try, right? Example 7, 8, 9. And almost most importantly, I've set up some word problems for you to try to tackle on your own. I'll post the solutions when I post the notes. So you'll have the solutions, but setting up these systems, right? Something like this or something like this, right? That's kind of the hardest part. And then you know how to solve these things, right? And so being able to translate a word problem into a system and then solving the system of equations, right? That's kind of a two-phase process. Yeah? But I want you to try it and see how it goes. So, hope you have a wonderful long weekend or have had a wonderful long weekend, and I'll see you on Friday next week. Stop the recording.